The northern lights, also known as Aurora Borealis, are a breathtaking spectacle. Imagine vibrant hues of green, pink and purple dancing across the night sky. This celestial ballet is not magic, but a beautiful display of physics in action. It all starts with the sun, our very own star. The sun is not a quiet giant, but a dynamic and active entity. It constantly emits a stream of charged particles called solar wind. Sometimes the sun releases massive bursts of energy and particles known as solar flares or coronal mass ejections. These charged particles from the sun travel through space at incredible speeds. When they reach Earth, they encounter our planet's magnetic field. Think of Earth's magnetic field as an invisible shield, protecting us from the sun's constant barrage of particles. This interaction between the solar wind and Earth's magnetic field is what gives rise to the mesmerizing display of the northern lights. The sun is a giant ball of hot gas, mostly hydrogen and helium. It's constantly undergoing nuclear fusion, converting hydrogen into helium and releasing a tremendous amount of energy in the process. This energy powers the sun and sends a constant stream of charged particles out into space. This stream is what we call the solar wind. The solar wind is not always constant. Sometimes the sun releases sudden, intense bursts of energy and particles. These are called solar flares. Solar flares are like giant explosions on the sun's surface, and they can release as much energy as billions of atomic bombs. Even more powerful than solar flares are coronal mass ejections, or CMEs. CMEs are massive eruptions of plasma and magnetic field from the sun's corona, the outermost layer of its atmosphere. These eruptions can send billions of tons of material hurtling into space at millions of kilometers per hour. When these charged particles from solar flares and CMEs reach Earth, they interact with our planet's magnetic field, creating the stunning displays of the northern lights. The intensity and frequency of the auroras are directly related to solar activity, with more frequent and brighter auroras occurring during periods of high solar activity. Earth's magnetic field acts as a shield, deflecting most of the sun's harmful radiation and charged particles. Imagine a bar magnet inside the Earth, with its north and south poles roughly aligned with the geographic poles. This magnetic field extends far out into space, forming a region called the Magnetosphere. The Magnetosphere acts like a giant shield, deflecting most of the charged particles in the solar wind around our planet. It's like a protective bubble that safeguards life on Earth from the sun's constant barrage of radiation. However, the magnetosphere is not completely impenetrable. Some of the charged particles from the solar wind manage to enter the Earth's atmosphere, especially near the poles where the magnetic field lines converge. These particles then collide with atoms in the atmosphere. When these charged particles from the solar wind collide with atoms in Earth's atmosphere, they transfer some of their energy. This excites the atoms, causing them to release light. This is the same basic principle behind neon lights. The color of the aurora depends on the type of atom that is excited. Oxygen atoms, for example, emit green or red light, while nitrogen atoms emit blue or purple light. The most common color seen in auroras is green, followed by pink, a combination of green and red. The shape and movement of the auroras are influenced by the Earth's magnetic field and the energy of the solar wind. Auroras can appear as curtains, arcs, spirals, or diffuse glows, constantly shifting and changing. The intensity and activity of the aurora can vary greatly, from faint, shimmering lights to brilliant displays that illuminate the entire sky.